Hi class, we're going to be looking over the last section of this Computer Foundations unit entitled Computer Architecture. So if you recall, we used transistors, tiny transistors that turn on and off, and together we stitch them together and we can build logic gates from them, and we talked about these 7 different types of logic gates. And then from there, we just saw how that we can combine these together into things like adders, into things like memory, and then we start putting them together into an entire computer. Now also remember that we defined a computer by this simple definition of any machine that takes in some sort of input, following some sort of instructions, some sort of programmable instructions, and generates some sort of output. Now, all this data, we talked about transistors being binary devices, computers being made out of transistors, and therefore computers are just binary by nature. All this data that we're talking about, input data, output data, the program itself, it's all data. It's all binary data. They're all just numbers. And we store all of that together in one big chunk of main memory. And so the CPU is constantly reading input data, reading instructions, and then writing out output data over and over and over again. We're going to talk about main memory a little bit, and then we're going to talk about the CPU a little bit to kind of finish up this unit. So main memory. Main memory basically is the holding place that stores all the ones and zeros of our input and output and instructions. So, here's a picture of memory, some numbers maybe. Maybe we have some colors here. Maybe we have, I don't know, some characters here. Maybe we have some instructions here. Notice, you really cannot tell just by looking at the ones and zeros. Are they numbers? Are they characters? They all look the same, actually. So the computer program itself knows. It says, okay, I'm going to put some integers here. I'm going to put some characters here. We're going to put the instructions here. And so that's how you know. But otherwise, you just can't look at it and distinguish what are they. So the CPU is constantly reading and writing to main memory. And when it does that, it always writes in byte chunks. Computers don't write to individual bits, but instead it reads and writes entire chunks, entire bytes. Commonly, computers will access multiple bytes, 8 bytes, 64-bit chunks all at the same time. Now, to access the memory, we need some sort of mechanism. And just like, we have millions of homes in the United States, and to get your mail to a certain home, we provide an address. Same thing with memory. In a computer, we have billions of bits, billions of bytes, and to access any one of those bytes, we need to specify where in my main memory do I get it from. So we have this notion of a memory address, and it's just sequential in nature, address 0, address 1, and by convention, we're always using hexadecimal number systems to specify the address that we're interested in. It makes it more readable. That's why we use the hexadecimal number system for readability. Okay, memory address size. The older computers, 32-bit microprocessors, the adders were 32 bits, and it was very natural then for the addresses to be 32 bits long. And so therefore, we have kind of a limitation of 4 gigabytes of main memory to access. 2 to the 10th power, that's a kilobyte. 2 to the 20th power is your megabyte. And then your 2 to the 30th power is your gigabyte. And so since we have 2 to the 32nd, 2 squared times 2 to the 30th, that gets us our 4 gigabytes. But actually, that's kind of limiting. There was a time when we never thought we would need 4 gigabytes of memory. But actually, we do, and we need even more than that nowadays. Here is a picture of a memory module that is 4 gigabytes big. So to access more than 4 gigabytes, if I want 16 gigabytes in my PC, I need more address bits. So nowadays, our 64-bit processors, technically, they can maybe address 64 bits of addresses. But that's a lot. And actually, I do believe we will not need more than 64 bits of addressing. I could be wrong, but it's a huge number. We have adequate number of bits nowadays for addressing all the memory that we want. Okay, so let's look at some examples of how a CPU would read and write. When a CPU wants to get information from main memory, it sends a command. It says, I want to read. It tells you how much it wants to read, and it tells you from where it wants to read. And so I want to get it from this particular address. I want to get 2 bytes in this case, and I want to send it back to the CPU. So you notice how over on the right hand side I have it written in binary just to kind of mix it up. But then I returned it and I wrote it as a hex. But you see how I break it up into these 4 bits here, 4-bit chunks, which is in this case 44. And in this other case here for this other byte we have A and we have 0. A write situation is the same thing. In this case we have a command. We have the data which we want to write, and we have the where. So in this case, this is our address, and we want to overwrite this value with this new value F2. So again, I wrote it in hex and binary. This is our F, and this is our 2. Okay, so that's how a CPU reads and writes data. A command and an address. Let's look at now how a CPU kind of cycles through instructions. Now instructions are stored in main memory, and typically they're stored sequentially, say address 1, address 2, address 3, 4, etc. And you have instruction after instruction after instruction that the CPU executes. It follows this cycle. Step 1, we fetch the instruction, and think of that as a read. We need to read from memory. Step 2, we get the instruction from memory, and now we need to decode it. It's a bunch of 1s and 0s. What is it? So the CPU needs to look at it, and using all of its logic gates, it figures out what type of instruction it is. And then step 3, we execute it. We do the instruction. And this repeats over and over and over again very fast at a speed of a gigahertz or beyond. And in all of our CPUs, there's kind of this notion of a clock that is given to the CPU that is telling it to do work. And it's not like a clock on the wall, but actually what it is it's this voltage signal that moves up and down. 0, 1.2 volts, 0, 1.2 volts, up and down constantly. And every single tick of the clock, you could say, this entire cycle happens. How fast is it? Well, we have 1 billion cycles a second. So the period, if we take the reciprocal, 1 over the frequency, is 10 to the negative 9th seconds per cycle. That means the length of one period here is 10 to the negative 9th seconds, or I'm going to write it as 1 nanosecond. That's for a gigahertz speed. You can actually imagine some of your laptops are running 2, 3 gigahertz, so it's even a fraction of a nanosecond. Okay, let's talk about instructions now. Instructions in a CPU are just bit patterns, zeros and ones. How long are they? Typically, typically I'll say 32 bits in length. They're always, in byte chunks, 1 byte, 2 byte, 3 byte, 4 byte. I'll just say this is our typical length. I mean, like I said, you could have 1 byte instructions. You could have 2 byte instructions. It really depends upon the CPU. It could be larger than 32 bits as well. How many instructions are there in a CPU? I would say typically in the tens to the low hundreds. 50 to 150, 50 to 200. Some computers, they might have thousands of instructions, but typically this might be the general range. Now, instructions in a CPU are actually very, very, very simple. And I want to give you an idea of what a CPU instruction is like. A CPU instruction, you have some what's called memory type instructions. They load or store data to and from memory. And so load is just another word for read. I want to read some data from memory. Store is just another fancy name for writing to memory. So write. So these are our memory operations. Very simple, reading a byte, writing a byte. Then we have a set of math instructions. And so we could add some integers, multiply some floating point, do some division, all sorts. We can AND, we can OR instructions, but I will label these as math instructions. Simple math instructions. And then I'll label these other types of instructions as control. Instruction control, in fact. So I'll label it as instruction control. So what this does is it tells the computer how to change the flow. And so it might say branch or jump to a different address. So remember I said typically the CPU will be executing sequentially one instruction at a time. 1, 2, 3, 4. But sometimes I don't want it to be sequential anymore, and I want it to jump to some other place in memory and get the instructions from somewhere else. So in this case, I might execute a jump instruction which tells it to jump somewhere else. Or I might even have a fancier thing called a branch. And a branch is kind of your conditional jumping. So I might have a branch right here. And it says, depending upon some situation, I want you to maybe go to another area of memory and start executing instructions from there instead. Or just continue on doing what you were doing. So again, instruction control kind of helps define where should I go in my instruction program. Okay? So all these instructions that the CPU understands, the name for that is machine language. A bunch of ones and zeros. So these are 2 bytes that might form one instruction command. And I might have these 3 bytes here that form another instruction command. And it looks quite hard to program, just ones and zeros. In the old days, we had to, maybe use switches to program everything into the computer. And then later on, we had punch cards, and they had holes in the punch card to indicate your zeros and the ones. But this is very hard to do. Actually, nobody, I don't think, really programs in machine language. But there is another language very closely tied to machine language. It's called assembly language. And this language is a human-readable version of machine language, such that you can, in a ways, write in machine language by writing in assembly language, because there is a one-to-one relationship. Every line in assembly language is one machine language instruction. So what you do need to have is you do need to have some sort of translator that takes your assembly line and converts it into the instruction. And so instead of using the word translator, we have this word in computer science called compiler. It's a translator that turns some language, written language, into the language that the CPU understands. So you could actually kind of guess what this means. This means store. This means increment, multiply, jump, load. And you can see here it says jump to the top. And this one here you might not be able to guess, BEQ, but this is a branch, and it says branch maybe to the bottom. Okay, now you don't need to memorize any of this, but the concept is it's human readable. It's the way that today there are people who still write code in assembly language. We write assembly language code to get very fast code or to get very small code, very tight and compact code. So there are still people who will do a little bit of machine language or assembly language coding for that purpose. Okay, but most people, actually the bulk, probably 99.9% of programmers do not program in assembly language, but what they do program in is a higher level language. In the old days, we had Fortran, we had Pascal, we had C, we had COBOL, which, funny, we still use today in the government. But nowadays, we have the more kind of modern languages like Java, Python, Swift, C++. I would actually say C is still quite a modern language. It's still in use today. It has evolved to C++, but C is still very, very useful. Now, all of these high-level languages do need some way of converting it to machine language because they're not readable as it is. This is not readable by the computer. The computer only understands machine language. So we must need to have some sort of translator to translate it ultimately into the machine language. And that translator is called either a compiler or an interpreter. They do the same thing, but they do it differently. Now, a compiler, what does it do? It's as if a publisher had a book that was written in English and they needed it translated in Spanish for, a different country. It would then hire some people that would then translate the entire book into Spanish. That's what a compiler does in the kind of computer world. It takes the high-level language program and converts the entire program all at once into machine language. It does the full thing. Now, you have an interpreter that's different. The interpreter, on the other hand, it's as if you were to visit another country. If I were to go to China, I don't speak Chinese. And so I would need an interpreter. And I would tell the interpreter a single sentence. The interpreter then translates and speaks it in Chinese. And then we repeat sentence by sentence, sentence by sentence. Now, an interpreter in a computer works the same way a human interpreter works. Instead of sentence by sentence, we have line by line. One line of Python code gets converted into, some instructions in machine language. And it repeats it over and over and over again. And you can imagine that because it's interpreted, if you have ever worked or talked through an interpreter, you know it can actually be slightly frustrating and slightly slower than a compiler. But I will say it's not that bad. It's actually, you'll find we're going to be running Python. Python is an interpreted language. And it's pretty fast. You won't really notice any difference. We're not going to be using a language like C. C is a compiled language, and it, of course, runs very fast. But you really won't notice a difference in general in the kind of stuff that we're going to be writing. Why might you use an interpreter? You could say it might be slightly easier to debug. When an error happens, you can kind of stop it right at that point. But I would say another reason is you can type one line of code and actually have it execute. You see the results. You type another line of code and you see the results. So it's actually very interactive. You don't have to write your entire program to run it. You could kind of type in a few lines of code and actually see it run, then type in a few more lines of code and see it run. So there's an interactivity that you just cannot ever have with a compiler. So that would be probably the bigger kind of benefit of an interpreted language. Okay, that's it. This kind of finishes up our computer architecture lesson today, as well as our entire unit on computer foundations. Okay, have a great day, everybody.